All right, today we're going to talk about phase changes. And with phase changes, we like to see from a solid to a liquid to a gas. And I want to talk about how the energy of those phase changes changes as we start to see those changes happen. And I'll explain that a little bit more as we go. But today, we have, if you could see in there, we have snow, okay, right? Snow, which represents a solid, and I'm going to go ahead and to put my thermometer in there, and then every 5 minutes, we're going to take a temperature, okay? And every 5 minutes, we're going to take a temperature of what it's going to be, and we're going to see what happens. I think you guys kind of already know what happens, but there's a couple things in there that are making it very unique that you wouldn't really suspect. Okay, so right now I have my thermometer in there at the beginning time, and I don't know if you can see it or not, but it looks like it's at about 2 degrees. Okay, at 2 degrees. All right, I'm going to set my timer for 5 minutes here, and then 5 minutes I'm going to come back and we're going to see what that temperature is. Okay, we're going to see what that temperature is. I want you guys to make a prediction in your head. What do you think that temperature is going to be after 5 minutes as it's sitting on my hot plate here? Okay, sitting on my hot plate. What's the temperature going to be after 5 minutes? All right, now we're at 5 minutes. And let's see what's happening. You can see that the snow is now water, right? It's turning to water. But let's see what our temperature is. Well, our temperature still doesn't look like it. You'd think that, that heat would make it higher, but it's really not any higher, is it? It's still about, let's say 5 degrees. So we only went up 3 degrees in that first 5 minutes. Okay, let's try the next 5. Let's try the next 5. All right, our next 5 minutes is up. Let's take a look at what it looks like now. Almost all water. We still have some snow in there, still a little bit, but we're not all the way to water yet, are we? We still see that there's some snow, some solid in there. Let's take a look at our temperature. Ooh, our temperature has gone up, but not that much yet. It's still only at 12 degrees. It's about 12 or 13 degrees. All right, 12 or 13 degrees. All right, let's give it another 5 minutes, and we'll see what it looks like next. All right, another 5 minutes. Okay, let's take a look at what our water looks like now. Okay, pretty much the same as it did before. We still have some solid in there with some ice, and we still have a little bit of water in there. Let's take a look at our temperature. Oh, our temperature's going up, though. Look, our temperature's going up. 30 degrees. It's almost 38 degrees, 30 degrees now. Okay, but still not super warm. Okay, it's still not super warm. All right, we'll set our time for another 5 minutes, and we'll see where we're at. All right, here we are again, 5 minutes later. Snow is gone. The snow is gone. Now we just have water. We just have water. And I bet you that temperature has gone up so much. Let's take a look at that temperature. Oh, yeah. Look at our temp. Our temp now is 50 degrees. Looks like 45. It's going down. As we speak, it's going down because it's not in the water. Okay? All right, let's do another 5 minutes. All right, another 5 minutes has passed. Let's take a look at it now. Now we are all water, and it's looking pretty hot. It's looking hot. I can feel that water vapor coming up from the... If you were here in class, you'd be doing this in class, you could feel that water vapor coming up. So let's look at that temperature. I'm going to pull this out. It's going to come down a little bit. but if you see, it was at like 74 degrees Celsius when I put it in there. So it raised about 20 degrees. I don't know if you can see it. You can see it going up now. See that? We're at about 72, 73 degrees Celsius. Okay, and we're going to keep rising. It's just keep going up and up and up. All right. All right. I'm going to give you another timer here. Let's go for another 5 minutes, and in this 5 minutes, then we'll come back again. All right. Bye. All right, next 5 minutes is up. Our water is getting hotter and hotter. We could see now it's starting to bubble. Okay, it's starting to bubble. We're getting some evaporation in there. Those water particles are getting up there. If we take a look at our temperature, I don't know if you can see it, it's at 90 degrees Celsius. It's at 90 degrees Celsius. Okay, 90 degrees Celsius. All right, let's give it about 5 more minutes and see what happens. You guys should try and start thinking. It's like when you're making macaroni, right, at home. It's about time to put those noodles in there. All right? All right, here we go. Another 5 minutes. All right, now, another 5 minutes. You can see it's boiling. You can see that the water's bubbling. We can see now the temperature, if I can get the temperature here, is about 98 degrees Celsius. 98 degrees Celsius. All right, now let's see what happens. I'm going to give another 5 minutes. What do you think is going to happen in the next 5 minutes? Let's find out. All right, our last 5 minutes here. It's probably almost been longer than I doubled it. And you can see here that we got condensation on our thermometer, the cool thermometer, but you would think that the temperature would continue to rise and go hotter and hotter and hotter and hotter, but yet it still only sits at, at 98 degrees. Okay, it sits at 98 degrees Celsius. Now, if you know anything about water boils at 100 degrees Celsius. Now that's pure water. It's pure water, not like this wasn't pure water at all. Like if you saw the chunks of dirt that were in it before I put it in the water, you would see why it was not pure water. But that water will boil and boil and boil. So I always ask people, do you think water can get any hotter than 100 degrees? And they say, oh yeah, it can. It can get hotter. It can get hotter than 100 degrees. Well, that's not true. It can't get hotter than 100 degrees. It cools. I mean, it doesn't. It just turns into. It changes state. It changes state into a gas. And I say the same thing. I said, can water get any colder than 0 degrees Celsius? And they say, oh yeah, it can. It cools. It cools. It gets colder than that. I mean, it's like 30 below outside. And when it's 30 below outside, then that's hotter, or that's colder. That's colder. Well, it can't. Okay, water can't get any colder than 32 degrees Fahrenheit or 0 degrees Celsius, because then we change state. It changes state. All right, and that's kind of what that whole lab was trying to teach you, is that water can't get hotter than 100 degrees because it changes state. Can't get colder than 0 degrees because it changes state. Stays at a solid. You can't change it anymore. Okay, and that's where those melting points and those boiling points. And we'll talk about more of this in the graph that is included with this lesson. All right? So when you look at this graph here, we see these lines, these vertical lines go up. We see these uneven lines for temperature. And we see it go up again, and then we see this uneven line for temperature again. So when you take a look at this, you'll see that when we start here, when our temperature is really low, it's still a solid, right? We're at a solid. This is like our 0 degrees Celsius or our 32 degrees Fahrenheit.
as we add heat, okay, as we add heat, our heat starts to go up. We still stay as solid, still stay as solid, solid, until we get to this point. And this point is called its melting or freezing point. Now, when we get there, it'll stay at that same temperature. So like when we looked at our graph to start, we had that, or when we did our project before with the snow stayed about the same temperature until all of the snow melted. The energy went to changing all of that snow. Some of that water, you think that, that one water molecule may be like 80 degrees. That's not true. That's not how this works. So all that energy is used to create everything. We have to change all of that stuff. We have to change all of our solid into a liquid. And once we change all of it to a liquid, then we see that liquid, that temperature start to come up. Starts to come up, starts to come up, starts to come up, starts to come up, until we get to that point where we get all of that water. We'd have to change all of that water, all of the water, okay, at 100 degrees Celsius. We have to change all of that water to a gas before we can start to get that gas to be hotter than 100 degrees Celsius. And we didn't get that in our experiment. I mean, we couldn't do that in our science classroom. But how we would have to change all of that stuff, all of it, to that certain point before we get to a gas. We can do this, talk about the same thing coming down. When we get a gas, let's say a gas is in the room, all of that gas has to change. Okay, all of that gas changes over to a liquid, and then all of that liquid has to change down to the temperature of 32 or 0 degrees Celsius before it then starts to freeze into a solid. So we drop our temperature, but then all of those water molecules would have to change to that temperature before we begin to turn to a solid. You can't have one molecule that's like 50 degrees and another one that's 32 degrees. That just wouldn't make sense. So that's how this graph represents this. And this is going to be on your test. And how we have this solid and like these flat points right here, these flat things, this represents of changing all of that solid, all of that solid gets to a certain temperature, and once all of that temperature is getting, then it turns to a liquid. So these flat parts, and we go solid, and then we have this melting point, okay, and then we come up here and we go to this boiling point. We can also say it the other way around. We have this condensing, and then we have this freezing point. Melting and freezing and vaporizing and condensing are the same things. I'm going to show a little video after this of someone else explaining it. Hopefully that'll help you. It'll help you understand it a little bit more.
Scott with some notes about phases of matter and phase changes. So we'll go over what those phases actually are and how you get from one to the next. So let's start with the types of matter that I'm sure we're all very familiar with, that we've all come to know and love. Our first state of matter are our solids, and in a solid you have atoms that are very close together, they're very tightly packed. These have a fixed volume and shape. So this marker is a solid. It's marker shaped, it always is, regardless of what I do with it, and it takes up a certain amount of space. These solids during this phase of matter have relatively low amounts of energy. So remember, atoms are always moving around and vibrating and whatnot, but in solids, they're not moving quite as much. They're never perfectly still, but they just like to hang out together. All right, our next phase of matter are liquids, and in a liquid, atoms are more spread out than in solids, so they have a little more space to work with. They have a fixed volume, but assume the shape of a container. So if you have a glass of water, that water will take up a certain amount of space, and that does not change, but it's going to be shaped whatever the shape of the glass is, that's what the water will assume it shape-wise. These particles have medium amounts of energy, relatively speaking, so they're moving around a little bit faster than they were with solids, which allows them to spread out a little bit more. Our last phase of matter that we're going to talk about today, and there are more, but the last one you need to know for today are the gases. And in a gases, the atoms are very spread out from one another because they have high amounts of energy. So these atoms are just zipping around, so they spread out far from each other. They have no fixed volume or shape. So if you picture all the air that's in the room that you're sitting in right now, I could take all of that and compress it down so that it took up a smaller amount of space. I would have to pressurize it, and that's a different set of notes entirely, but I could do it, and it would assume the shape of whatever container it's in. So those are our states of matter. Now we need to look at something that you'll see later on. This is what's called a phase change diagram or graph. And this shows us what happens with matter as we increase the amount of heat energy and what happens to the temperature, respectively. So we see here with solids, they have low amounts of heat energy. That means the atoms aren't moving around. So they would kind of condense like this, there wouldn't be a whole lot of space. As you add energy, you see these areas where it's flat. These are our actual phase changes. This is where we go from one state of matter to the next, either by melting a solid into a liquid, boiling a liquid to a gas, or going in the opposite way, condensing gases to liquids and freezing liquids to solids. The interesting thing about this, or the thing that you need to learn from, or that you need to get from this particular set of notes, is that during a phase change, so during this time period, temperature stays the same. What doesn't stay the same is heat energy. So heat energy is either added or released, depending on which way you're looking at. I'll move that up so you can see that. All right, so temperature is staying the same, which might seem a little counterintuitive. We know we have to heat up a solid in order for it to become a liquid, but what we don't see is that during that time where you have some solid, some liquid, that temperature is going to remain constant. The temperature itself will not increase until I fully change to the next state of matter. Okay? So, the other thing you need to be able to use or be able to interpret from this graph is a phase change endothermic or exothermic. If you remember from our chemistry or chemical reactions unit, something that is exothermic releases heat energy. The reaction loses that energy to the environment. And in an endothermic reaction, heat energy is absorbed from the environment. So we would have to look at this axis down here to tell if it's endothermic or exothermic. So let's take a look at melting and boiling. For both melting and boiling, I am adding heat energy to the system. I'm adding energy that makes these atoms move around faster. So these processes are endothermic. I have added heat energy to them. Let's look at condensing and freezing. So during these phase changes, and this might seem counterintuitive because we know when we freeze something it becomes cold, and we typically associate cold with endothermic. What's happening is heat energy is being released from these atoms to somewhere else. So these are actually exothermic because I'm reducing the amount of heat I have. I'm releasing that heat.
All right, the last part of our lesson here. This is what you have to do in your packet. So we take a look at our packet here. You can see that I put my intervals down for my time. I went 2, 4, 6, 8, 10, 12, all the way up to 40 minutes. Then for my temperature, I went up by intervals of 10, 20, 30, 40, 50, 60, 70, 80, 90, and to 100. As you can see, when you look at that chart there, that when we were at 5 minutes, we were at like 3 degrees. When we were at 10 minutes, we were at 12 degrees. When we were at 15 minutes, we were at about 27 degrees. When we were at 20 minutes, we were at about 52 degrees. When we were at 30 minutes, we were at 80 degrees. When we were at 35 minutes, we were at 92. And then when we were at 40 minutes, we were at 98. So you need to fill those out. I put those main pieces in there where the melting point, where our liquid was, and then where our boiling point. And then answer the question down below. What are some key patterns you noticed with the snow as it changed phases in temperatures?